Yeah, we should be able to tell by looking at scores. I mean, usually some people get a whole lot by the end. Let's take a look. 123 is here, and the scores are there. And over here's the cahoots. There's people with 21 and 30 and stuff. So yeah, it can add up. All right. And I ought to mute them so they don't annoy each other. All right. Good. Looks like it is time to resume, so I'll bring this back up. Okay. So we talked about symmetric encryption, the old stuff, and asymmetric encryption, the new stuff. And it turns out there's one more thing you need, which is hashing. Hashing is basically a way to put a fingerprint on a file so you can tell if it changed. So you take a message of any length and you somehow combine all the bits to make a number that is just a fingerprint to tell you if that file has changed. Now, the first simplest thing was called parity. This is why ASCII only uses 7 bits. You would send bytes 8 bits at a time, you would send 7 bits, and you would choose to be even parity or odd parity, and the last bit would make the total number of ones either even or odd. So that if you lost 1 bit while transmitting it, you would know that because the parity would be wrong, and you'd go to request a resend of that byte. That was the simplest error correction method. That was a 1-bit hash. That, of course, would detect certain kinds of errors, but it would not withstand a malicious attacker, because a malicious attacker could easily calculate what value to put there to make valid hashes. So then we had CRC32, which is what Ethernet uses at layer 2. When you get a frame by Ethernet, it checks the CRC32, which is a hash, to see if that frame has been altered. And CRC32 is good at detecting transmission errors, but it is too short. As we've now talked about, people can easily break a 32-bit key by trying all 2 to 32-bit values, so an attacker can forge a CRC32 hash. It only detects accidental errors. So this is the issue of collisions. Suppose I have a hash that is just some number of bits long, like 100 bits. If I feed in data that is longer than that, like 100 megabytes, there are millions of files that must cache to the same value because there aren't as many hashes as there are files. So it is always the case that a hash cannot be reversed in principle. There are many files that hash to the same hash. But what you want to do is choose a hash that is so long and so hard to predict that nobody can find any of them. So there'd be no known collisions. Collisions should be so rare that even if you hunt for them with all the computers in the world, with all the time in the world, you won't find any. Then you can treat the hash as effectively unique. Like, fingerprints are like this. You take fingerprints out there. There is some chance, of course, that 2 people would just happen to have the same fingerprint. But it is so rare that it never happens in practice, and we can trust the fingerprint to tell who's been doing things at a crime scene. That's what you want here. MD5, MD4 was invented long ago, and MD5 came after it. And MD5 was in popular use as a hash value, but it was never approved by the government. The National Institute of Standards did not get in the business of approving cryptographic routines until fairly recently, and by the time they got around to deciding they would declare a good hash system, MD5 was already broken. So they had a contest to find a better hash algorithm, and they decided that that would be SHA, the secure hash algorithm. Just like AES is the advanced encryption system and DES is the data encryption system, these are stamps of approval that the government puts on something after it wins the contest to get the official approval. And this was NIST, which was SHA1 was the system. So you can do these very easily in Python too. All you do is import hashlib. The reason why Python is everybody's best friend is because there are libraries that do all the work for you. So I can take a password like this, the one we use a lot, an old Microsoft password, and you can do hashlib.new of MD5, for example, on P. And if I do that, I'm just going to get some binary junk. I'd rather see it in hex. All right, that is an MD5 hash. It is 128 bits long. Always the same length, doesn't matter what you feed in, and always get the same result. Now, if I were to change anything about the password, like change the D to an E, and then hash it again, everything changes. 161 EB, E947, that's what a hash is supposed to do. It's not got any pattern, you can't deduce anything about the password for this hash. It's not in cryptography. You cannot reverse it and get back to the message. It is just a fingerprint. And if you transmit it to the other end, then the other person can calculate the hash and compare it to what was transmitted. And if they don't agree, they know something got garbled. Either the password got garbled or the hash got garbled in transmission. So they would send a response saying, that message did not get me resent. And that's how you do it. Now you can use SHA1 also with just the same library. So let's go back to my first password and see what the SHA1 looks like. You can see it looks just the same, it's just longer. SHA1 is 160 bits, which is a little bit longer than 128. It has the same desirable property that if you change even one bit of the input, it changes half the bits at random. Everything changes. So it's just another way to put a fingerprint on a file. Now there are longer ones. I don't know if I can do SHA-256. Let's give it a shot. If I go back to this one, SHA-2 came out years ago and was approved, and it had different links, but one of them was SHA-256. Yeah, there you go, twice as long as MD5. Getting really long and kind of annoying. But again, if you change even one bit of the input there, yes, sir, Macs and the and Linux use SHA-512 to encrypt to hash passwords. And I guess if I have 256, I probably have 512 too, which is technically one of the, yep, there's 512. So long it won't even fit on the line. So it's getting kind of ridiculous, but as you can imagine, it's real hard to find two files that hash the same one of them. All right, so SHA-512 is very secure. SHA-1 was considered secure until earlier this year when it got broken. In February 2017, Google found a SHA1 collision. The original point of SHA1 was it's 160 bits long. You should have to try 2 to the 80 files before you ever find a collision. This goes by the square root. So that should have never happened, but there were some mathematical defects in it. So there were ways to shorten it a little bit, down from 2 to the 80, down to 272, down to the 2 to the 60 something to where they could actually do it. So there are 2 files here, and let me bring them up. I've downloaded them. These are the 2 files that Google announced earlier this year. They made it so you can download them and play with them, although I was not able to, I downloaded them earlier, but I was not able to re-download them today because I think antivirus on the network blocks them. They are considered evil because they have this property of defying hash algorithms. So I think they're visible. So they're called shattered. And I thought I left them here. Let's put a search here. There we go, not there. All right, pardon me while I go to figure out where I hid my stinking files. Maybe I put these where I intended to put everything, which is in the projects folder. All right, they should start with shattered. And there they are, 2 files. Okay, let's see what they look like. There's one of them. And there's the other one. And you can see they're not the same. One is red and the other is blue. And, okay. And let's see how big they are. I thought I had the size here, but I can find it with get info. So this one is 422.435. And that's shattered 1. Shattered 2 is exactly the same size, 422.435, but they're clearly not the same contents. And so let's hash them. So we leave this and go to that directory, which is box, website, 123, project 14. Okay. And now I can do MD5s this way, and I can do, it's SHA-SUM of the file, and I can do shattered, there, shattered1.pdf. So there's the SHA of that file, 38, 76, and so on. And if I do the SHA-SUM of shattered 2, it's the same. And I know they're not the same, and I can see that by doing the MD5 of them. There's the MD5 of shattered 2, and there's the MD5 of shattered 1. They're completely different. The files are different, but they have the same SHA. This should never have been possible. You should have been able to hunt until the end of time with all the computers in the world and never find one. That was the goal of the SHA1 algorithm. That's why they called it secure. But it had defects, and they had more defects, and cryptographers kept finding more ways to get in until Google finally cracked it earlier this year. People saw this coming about 2 or 3 years ago, and they started saying, we better quit using SHA1 because pretty soon somebody's going to crack it, and we got to go to SHA2, which is now being enforced by most browser makers. If your certificate used by your website is based on SHA1, most modern browsers will refuse to make a secure connection. They will just warn the user, you can't trust this connection because these clowns are using out-of-date cryptography. So here's Google's announcement. Here they talked about it. It took them 6,000 years of processor time to do that. So of course they didn't spend 6,000 years on a processor. They spent 1 year on 6,000 processors or something like that. But anyway, that's why it needed a bunch of people in Google. Somebody with a lot of big computers could do it. But it didn't take all the computers in the world all the time in the world, which is what it should have taken. They were able to do it with a reasonable amount of computing time. So that's shattered, and they even gave a cute logo and everything and wrote a web page where you can download the files and play with them to prove that it's no good. So people saw this coming, and starting in 2014, various browsers started saying they were going to quit supporting SHA-1. And if you're trusting SHA-1, they're going to not let people trust your website. And by now, and starting this year, Microsoft, Google, and Mozilla all will not approve anything based on SHA-1. Forget it. You can't trust it, because if Google can do that in 6,000 years of computing time, who knows what the NSA can do, and the KGB and the Chinese government, and North Koreans and everybody else. You really just can't trust that stuff anymore. So you can go to this website if you want to test HTTPS certificates. It's kind of good, clean fun. It'll test for all kinds of cryptographic errors in certificates. And when I found this site a few years ago, I started researching things, so I went and tested colleges. See how many of them get a good grade. A minus, D. These colleges all got Fs by using really out-of-date stuff that was known to be broken. Then I tested banks, and there was a bank using an F-grade certificate. Then I went back in 2016, and now there were 4 Fs. Now, it's not that the banks got worse. It's that the standards went up. Like, you know, now I'm sure they wouldn't give you, they'd probably give you an F for using SHA-1 now, although in 2016 they probably wouldn't. But anyway, here's the 4 banks that were getting Fs at that time. This is why people often contact college and scream and yell and say I should be fired right away because I keep publishing this kind of stuff. Someone told me to try credit unions, so I tried the top 100 credit unions, and there they are. There's 5 credit unions in 2016 that are getting Fs by using out-of-date cryptography. And anyway, on it goes. I haven't retested the colleges lately. By the way, our college was always doing okay, like an A or a B. I would have told them. But we're pretty good about security around here. We're actually a lot better than most colleges. Anyway, so digital signatures, we talked about this. You make a hash encrypted with your private key, and now you have a signature which proves that you signed something and that here's the document that you signed. So that ensures integrity because it can calculate the hash of the document and prove that it hasn't altered, and it ensures authenticity. You know who signed it, and it ensures non-repudiation. I cannot deny that I signed it later because I'm the only possessor of my private key. At least that's assumed. So here's just a summary of what we talked about. The symmetric algorithms are the old-fashioned encryption, and this is mostly what people use because it's the fastest, most efficient way to encrypt stuff if you could overcome the difficult problem of distributing the key. So DES was the government-approved standard for a long time, but in the late 90s, utterly crushed and destroyed by various people proving you could brute force it. Now these others are all considered okay. Triple DES, AES are fine. Triple DES is fine, but it doesn't run as fast as AES on modern hardware. AES was chosen not only because it's secure, but also because it runs really fast on modern processors. They chose one that naturally fits the operations available on processors. And in fact, modern, Tom has shown me the source code for some Mac libraries. Modern Intel processors actually have special AES instructions in the machine language just to do it fast, because it is the standard and everybody uses it. And as far as anybody knows, AES is perfectly fine and wonderful, and it will survive everything. Even quantum cryptography won't get into the 256. So this looks like a real winner we can use for the rest of our lifetime without any worries, as far as anybody knows. But there's these others, in case you don't like it, like IDEA and Blowfish and RC5 are there if something should turn out to be wrong with AES, or if you don't like the government and you want to be sure and use something the government didn't put their sticky little fingers in, that you use these other ones. Diffie-Hellman, was the start of it all. You can exchange a key over an untrusted message, over an untrusted line. And because of that, you can now make an encryption routine based on it, which is RSA is the standard that everybody uses. ECC was the improvement to make it more efficient. And El Gamal, in principle, works, but it never was really implemented because the other two are good enough for all practical purposes. It's around in case anybody wants it. They're all considered perfectly fine today, but we are very worried that they're all going to fall in a decade or two when quantum computers really become available. Right now, there is no working quantum computer that does anything important, but all the essential components have been invented, and there are prototypes showing that this works and that works. But right now, they cost millions of bucks and have to be cooled to ridiculously low temperatures and only have a couple of bits. So they can't really accomplish anything yet, but if they manage to miniaturize all this stuff and make it a million times cheaper, then there will be quantum computers that can blast through this stuff like nothing. And there's hashing algorithms. MD2 and MD4 and MD5 came out a long time ago. They all have collisions. SHA1 came out and was considered safe for a long time, but now we know it has collisions and shouldn't be trusted, so SHA2 has never been broken. And it is much longer, as you saw, 256 up to 512. Unless there is something really seriously wrong with the math, it'll probably last a really long time. But if somebody ever manages to hack SHA2, they've already had the contest and approved a successor called SHA3 that should be even more secure, so it's waiting in the wings. As far as I know, nobody has actually built it into any system yet because SHA2 is working fine, but it's available. If anybody wants to use it, they've already got a good one. So it's a good place to be. There's the last cahoots. The rest of this chapter we'll do next time. So, cahoots, should be some cahoots available around here someplace. There they are. Okay. Yeah, this is already an hour and a half. I'm glad I broke it in half. Hey, oh, I have to hit a button. That's why nothing's happening. Okay. There we go. Somebody told me they got this music stuck in their head from watching these lectures. It occurred to me that I could try like putting in a browser extension and changing the music. If I get really bored, I might do that, but I got other things to do. I like it. Yeah, well, you know, it occurred to me it would be pretty easy to do like grease monkey. Change the music. But first I have to do QRadar. QRadar is my project, which is IBM's threat analysis system. It's really awesome, and I got it working. So North Korea, there we go. Boo, NSA. Yeah, a bunch of people, cryptographers are so mad at the NSA when this stuff came out, especially Stone. Dark Tangent rejected all the government papers at DEF CON and said, we don't want any government researchers coming to DEF CON this year because I can't guarantee your safety. Because people were so mad at the government, he thought they might get a pie in the face or punch in the face or something. And, that blew over. Next year, Keith Alexander, the head of the NSA, was at DEF CON. But for a year, everybody was really mad at the government over Stone. Anyway, I'll wait 5 seconds and do this. All right, 5 questions. So, which one of these does public key encryption? Okay, RSA is the standard public key encryption. The rest of these are private key encryption, and that's just hashing, not even encryption. All right, so which one of these does hashing? All right, MD5. MD5 is still commonly used for many purposes, even though it has had known collisions for years. Still, in practice, if you download a file and the MD5 matches, the odds are very good that nobody altered it. It's not perfect, but it's good enough for most purposes. Anyway, it is commonly used. All right, which one has no known collisions? All right, got two. SHA1 and MD5 have collisions, and RSA is not a hashing algorithm. This one here is the one that now we think about this one the way we used to think about SHA1. It looks perfect. This should last for 1,000 years. We should never have to worry anymore. But you know, whenever anybody says that, that's just a big kick me sign. You never know. Everything we trust, a few years later, say, what a fool I was to trust that. So we'll see what happens. Which one of these is 64 bits long? None of them, that's not enough at all. 64 doesn't do anything. It's like a CRC32, no hash function, 64 bits long, would be much good at all. Even MD5 is 128 bits long. All right, which one's 160 bits long? Okay, that's SHA1. 160 because the square root is 80 and 2 to the 80 is uncrackable, and they thought that would be fine. And it would have been fine, except there were ways to cheat and make it faster. So that's the winner. So Daniel Callahan has got 2. And Boo, NSA, and Turkey Neck are going to have to tell me who they are because those don't seem like real names. Are you guys in the room?
I'm Boo NSA.
You're Boo NSA, okay. And is Turkey Neck in the room? Well, then Turkey Neck better send me a chat message or something. Aha, a chat message comes in from Turkey Neck. Okay, good. I got your name. All right. And so I'm going to stop the share. I'll go to the lab and help anybody who wants to work here. But that's it. And